Hey everyone. So we are going to dive deeper and deeper into the proton today as we go through Thompson's 8.2. This should be a short ish section. We're just going to reformulate a couple of things and just in preparation for what we're going to learn before the end of this chapter, which are these parton distribution functions, which will allow us to figure out actually the quark and the gluon and the C quark and valence quark content inside the proton, and we actually can probe the structure inside the proton. Okay, so let's get started. So we are kind of in this intermediate phase where we have an electron coming in, scattering off a proton, but now that the wavelength of the photon exchange between the electron and the proton is short enough, we can actually see inside the structure of the proton. Okay, right. To quantify these interactions, right, we already did the calculation last chapter of an electron, and I put proton in parentheses here because, right, we're going to start scattering off stuff inside the proton instead of the entire proton itself. Okay, so we're going to start with the Rosenbluth formula. Right, the Rosenbluth formula is the differential cross section where you have this alpha square 1 over e to the incoming energy of the electron square. Right, you have this Rutherford factor from the sine to the fourth power. Okay, and we also have the Mott scattering, which contains both the charge coupling between the electron and the proton, and also the magnetic spin-spin coupling between the electron and proton. So just a reminder, right, as these particles are moving at relativistic speed toward each other, what happened is that the magnetic field actually dominates how much they scatter off each other as opposed to just the electric field. Okay. And then we have the purely magnetic part, whereas when we have added the recoil part of the cross section, we have the sine square theta term, okay, theta over 2 term, okay. What we're going to do is we're going to reformulate this once again in order to make it so that it makes more sense to quantify it in terms of the content inside the proton itself, okay. So as usual, like Q square, the capital Q square is defined to be negative Q square, right? Just as before, where we know that since this is a T-channel process or scattering process, the regular Q square, the lowercase q square, is always going to be negative, so it's more convenient to use capital Q square, which makes it always positive, okay? And then in the previous section, we defined this elasticity factor, and this is going to turn out to be very interesting. X, whereas Q square over 2 times the dot product between the incoming proton dotted with the photon exchange between the electron and a proton. Okay, the electron and the proton. Okay, and you have the inelasticity kinematic variable, where it's the dot product be P2 dot Q and then P2 dot P1 instead. And then we also have nu, which is basically going to be just the energy difference between the incoming and outgoing electron. But it can also be calculated in this invariant form, where it's P2 dot Q divided by the mass of the proton. All of these are invariant because, right, any 4 vectors dot product into each other are always invariant. And of course, mass is invariant, and then Q squared is also another dot product between the photon 4 vector dotted to itself. Okay. All right. So what we're going to do is we're going to recast this recast the Rosenbluth formula into these kinematic variables that we just defined last section. And then, there's a long homework problem to do this because it's going to take like an hour if I try to do this in a lecture. Okay. And what will happen is that once you do the substitution to calculate these in terms of the angle between them and stuff like that, what happened is that the differential cross-section, okay, will turn into, instead of being in the derivative, the differential in terms of omega, I mean, because remember omega d omega is basically sine theta d phi, right? And what happened is that when you do this change of variable, right, instead of depending on omega now, right, this differential cross-section actually depends on q squared instead. That's why you have this derivative relative to q squared. Okay, when you do the substitution there, what you'll see is that it's going to be 4 pi alpha squared, and then it's going to have a q to the 4th power on the bottom. Okay, and then you will retain these, charge coupling and magnetic coupling. So these terms basically stay the same, but this cosine square theta, you will find is actually 1 minus y squared over q squared, and then mp squared just for to get the units right. Okay, and then the sine squared term turns into just, along with this 1/2 tau, turns into this 2 times tau, turns out to be 1/2 y squared instead. So you can put that in there. Okay. So this is all going to be, I think, the second problem in the homework, where you get to do all this algebra to do this change of variable. Okay. So what we're going to do is we're going to lump these factors of GEs and taus and GMs, right? All this stuff. We're going to lump them all together into this factor called F2. Okay. And then we're going to make GM, right, basically F1, just to, make it the same thing, okay? Right, so these are known as structure functions, okay? So we're going to be dealing with multiple versions of this, okay? Okay, the reason they're called structure functions, they literally define what is the structure inside the proton, okay? Right. So right now we can think about the, F1 as kind of like the purely magnetic structure, and then F2 is sort of the charge plus magnetic structure combined together. Okay. Okay, so what we're interested in is actually, right, how does the cross-section change if we change one of the kinematic variables? Okay, we're going to change x in this case, and hopefully it'll be interesting. We're going to see why that's the right choice as opposed to y or nu and stuff like that. Okay, so what we do is we do another derivative, okay, on top of this. So this is known as the double. So this is known as the double differential cross-section. Okay, where instead of just the differential cross-section with respect to one variable, in the previous case q squared, right, it's going to be a differential cross-section with two variables. So you do a second derivative, right, with different variables. Okay, and then we're going to take this derivative with respect to dx, where x is this kinematic variable that we have up here, which is also related to q squared. When you do this, okay, you're going to move a lot of stuff around, but instead of trying to deal with that, what we're going to do is we're going to define yet another new set of structure function, capital F2 and capital F1, to deal with that. And because what happened is that these structure functions are actually not, just calculable, because the structure function actually depends on the strong interaction inside the proton, and therefore we actually cannot do any calculations with them anyway. So there's no reason to keep track of the functional form of it, because we can't write one anyway. Okay, and the structure function is going to depend on both, not just q now, it's going to depend on x, right, this kinematic variable, and then F2 is also going to depend on x, F1 is also going to depend on x, okay, and we bring in this little extra factor of x down here, okay, just to keep the units between these structure function, so they actually range from, to make the structure function have the same units. Okay. Okay. All right. So by comparing this to the Rosenbluth formula, okay. Okay. So F1 is the purely magnetic coupling. So hopefully that makes sense, right? Just from looking up here, I'm going to highlight the GM here. That's just the magnetic coupling, right? And then once again, right, as I mentioned this already, this is related to some combination of the charge and the magnetic coupling together, okay, not just the magnetic coupling by itself, okay? So we're going to do now, okay, we're going to go to a high Q square limit, okay, high Q square meaning, right, the momentum exchange square, the between the photon and the, between the electron and the proton, meaning the energy of the photon in there, right? It's going to be much bigger than the mass of the proton itself, times y squared. Just change to smaller pen size. Okay. When you do that, okay, right, q squared much bigger than this term basically goes away. Okay. Okay, when that term basically goes away, you end up with equation 8.12, which is that this double differential cross section, okay, once again is 4 pi alpha squared q to the fourth, and then this simplifies to just 1 minus y, while the rest of the equation stays the same. Okay, right? So now this double differential cross section, right, is, right, a function of q squared, okay, and going back to the previous section, right, q squared, right, is just 4 times energy 1 times energy 2, and the signs of the angle between the two, in between the incoming outgoing electron squared divided by 2 squared. Okay, and x is just a function of q and E1 and E3 again, and then y is actually 1 minus the difference between the ratio between the outgoing and incoming electrons energy. Okay, so this is, right, this function can be completely determined, right, if we can measure these three things, q squared, x, and y. In order to measure q squared, x, and y, right, we need E1, we need E3, and theta. And that's it, right? Okay. So, okay, since these these F1 and F2 are depending on the structure inside the proton, it's actually with the current formulation of the standard model and our current understanding of how we can do calculations using perturbation theory, where, remember the idea of when we did the quantum electrodynamics, is that we know that, if we do the lowest order diagram, right, meaning, maybe like we have electron muon scattering off each other, right? The reason we can all we have to do is make the calculation for this one diagram is because we know the next leading order diagram is going to be, the cross section for that is going to be lower by a factor of alpha, right? So whenever we do a calculation with the lowest order approximation or the first term in the perturbation theory, right, we're going to get the answer within, a little bit better than 1%. Okay, so that's why any higher order diagrams, we don't really have to worry about it. A lot of people, do like the 5th order approximation, so they get the answer within like one part in like 10 million or something like that. But every time you do that, you get more and more accurate answer. The problem with the strong force is that alpha strong, right, is approximately 1 for the energy range that we're interested in. And so therefore, in order for you to get an accurate answer for any strong force interaction, you actually have to add up all the infinite number of diagrams, because, right, you can always add more diagrams. For example here, right, I can add another photon between these things, right, because they're both charged. I can add another photon here. I can have this one spit out a photon. So you can add infinite number of these diagrams, right? For QED, it doesn't matter, because, right, every time you added another vertex, right, the cross section for that particular diagram goes down by by a factor of 100, and therefore you don't have to. You get pretty close to the answer with just the leading order. Or for the strong force, your answer is completely wrong unless you can add up these infinite numbers of diagram, which made it impossible with our current technology, not just like computer technology, but like our mathematical tools in order to calculate them. Okay, so so the structure function f1 and f2 are always just going to be so far has been only experimentally measured. Okay, and something interesting happened. Okay, all right, these f1s and f2s are almost independent of q squared. You notice that, right? It depends on x, it depends on q squared, right? What we're seeing in data is that there's almost no q squared dependence. Okay, as long as you're in this high energy, you're already at this high q squared regime. You're not, dealing with Rutherford or Mott scattering. You're probing inside the structure inside the proton. What happened is that, and I'm going to show you the plot down here from figure 8.4 from the book, right? So this plot is plotting the structure function that they're able to measure, right, as a function of q squared. You notice that it's almost flat, right? It's like, wow, that's pretty nice. Okay. It is not flat as a function of x, so there's this increase as you increase x, okay? And we're going to see what x is going to represent soon because of this situation, okay? So what this is indicating is that the structure function is actually telling you that the electrons is actually scattering off some point-like object inside the proton. So when people are experimentally seeing this, it's like, and then people say, oh, yeah, there must be something inside the proton that we're scattering off of that's acting like a point-like object. Okay. So in fact, F1 and F2 are actually related to each other through this Callan-Gross relations, where basically F2 can be calculated from F1 if you just multiply by 2 times the Borg the elasticity parameter. Okay, we're not going to call that the Bjork function yet. Okay, so essentially what you need to do if you're in experiment, if you measure F1, then you can actually just calculate F2. So all you have to do is just measure this F1.